Okay, so in this example, we're given a transformation from P2 to R2. So your input in this transformation is a polynomial, and your output is a two-dimensional vector in R2. So part A here is meant as a way of familiarizing yourself with the transformation, with how this can happen. How can a polynomial in P2 be transformed into a vector in R2? So as an example, if we apply this transformation t to the polynomial 4t squared plus 3t minus 6, then what needs to happen is first we find p of 0, which in this case would be 4 times 0 squared plus 3 times 0 minus 6. So 0 plus 0 minus 6, we get negative 6 for the first entry. In the second entry here, so this is supposed to be p prime at 2. So I'm following this definition here. So let me first write down, so p prime in this case would be 4 times 2, so that 2 would come down. So we get 8 times t to the first, plus 3 times 1 for the derivative of t. And then now if we substitute 2, which again, I'm just following the instructions up here that were given to us for this particular transformation, then this is 8 times 2 plus 3, so 16 plus 3, so 19. So this is how a polynomial like this, a quadratic polynomial, gets transformed into a two-dimensional vector here. So that's part A. Part B show that this is a linear transformation. Okay, so I'm going to clear what I've written so far. And let's talk about part B. So for something to be a linear transformation, there are two requirements. So for one thing, when you have a sum of two inputs, so in this case, let's say P1 plus P2, T of that sum should equal the transformation applied to the first part of that sum plus the transformation applied to the second part individually. So the sum, when you apply the transformation to each part individually, should equal the transformation of the sum of the two polynomials. So we want to show that that holds for this transformation. Oops, so I'm going to change back to black here. It's not, I'm having a hard time. I might just write in red. Oh, here we go. Okay, so T of P1 plus P2, according to the equation for this transformation, that's equal to the polynomial P1 plus P2 evaluated at 0, and the derivative of the polynomial P1 plus P2 evaluated at 2. Now, thanks to properties of polynomials, you can plug 0 into these individually here. So P1 plus P2 evaluated at 0, that is equal to P1 of 0. Whoops, I did not mean to zoom in, but okay. That's equal to, sorry guys, I'm still getting used to this. Okay, I had to pause there for a minute. But so P1 plus P2 evaluated at 0 is equal to P1 of 0 plus P2 of 0. That's just the way we evaluate polynomials, right? Like when I plugged in a number in part A, I plugged in 0 here plus plugged in 0 here. That's just always the way we evaluate polynomials. Also, I mean, the way we differentiate polynomials, you just take the derivative of the first part, so P1 prime at 2, plus the derivative of the second part, so P2 prime at 2. When we evaluate this value in the second entry here. So I could separate that into two separate vectors, P1 of 0, P1 prime at 2, and then plus a separate vector, P2 at 0, and P2 prime at 2. And so this is equal to T of P1 plus T of P2. And so it satisfies the first property of a linear transformation. Now the second property, let me list this up here before I, oops, okay. second property that has to be satisfied here is that t of a scalar c times the polynomial is equal to, we can pull the scalar out and write it as c times t of p. If t is a linear transformation, then you should be able to pull out scalar multiples, as well as distribute the transformation over a sum, like we did here. Okay, so I'm going to clear the screen again, and let me try to show that second property. Oops. Okay. So that second property for linearity, t of c times p, oops, and this will go quicker than the first one. So according to this definition of the transformation up here, t of c times p will be c times p evaluated at 0, and then c times p prime evaluated at 2. But so with each of those, I could pull the scalar c out. So this is c times p of 0, c times p prime at 2. I'm sorry for my handwriting. And we can factor c out of that vector overall, so that's c times p of 0, yikes, okay, and p prime at 2. And so this now is the scalar c times t of p. So that second property is satisfied, and that shows that t is a linear transformation. I'm going to solve this third part here in a separate video.